Hello, my lovely math students. I'm not able to be there today to teach you, so you get the next best thing. The same notes I was going to give you with my voice. So today we're going to look at a concept called indirect measurement. And really, it's just a different way to apply the stuff that we've been doing with similar triangles. So look at those cute triangles. They're in love because they're so similar. Alright, so let's do a quick review of how we solve for a missing side in similar triangles. So remember that when you've got a little triangle inside a bigger triangle, we call those nested triangles, and they are similar. So in this example, the smaller triangle has a height of 16, hypotenuse of 34. The bigger triangle has a height of C, that's what we're going to be solving for, and a hypotenuse of 68. 34 plus 34 is 68. So the proportion that I'm going to set up to solve this, I'm going to put the short side over the long side of the smaller triangle, and C, the missing side, over the long side, the hypotenuse of the big triangle. And what do I notice? How do you get from 34 to 68? That's a times 2. It's 2 times bigger. So if the hypotenuse is 2 times bigger, the height also needs to be 2 times bigger. 16 times 2 is 32. So the height of the big triangle is going to be 32. All right, hopefully that was a quick and easy review and something that you remember from our work last week. So we're going to take this idea, or what we've done with similar triangles, and we're going to apply it to a real life kind of situation. So this example that we're going to talk about here today is how can you measure something like the Statue of Liberty from the bottom to the top. So your options are really tall ladder, good, I guess, mountain climbing gear, rappelling gear, or maybe a helicopter could drive you up to the top, and you can measure that way. The way that we're going to talk about today is called indirect measurement, and that says that we've got the sun here, the sun's shining down, and these lines, the dashed lines there, are parallel. So we could plant a stick in the ground, measure how tall the stick is, and measure the stick's shadow. Now we're going to measure the Statue of Liberty's shadow, which is much safer. It's on the ground. We could just use our tape measure on the ground. Measure the statue's shadow, and then we've got these similar triangles formed by the stick and its shadow, and the Statue of Liberty and its shadow, and we can use the height of the stick and that ratio, the height to the shadow, to find this missing height compared to the statue's shadow. Alright, so if I was there today, you'd be watching this awesome video, so you're going to have to watch it even though I'm not there. If I can press play.
I can't wait to get home for lunch.
Kids, I'm home. Hi, Mom. Can you help me with a math problem? How can you use shadows to find a height that you can't measure directly?
Alright, as always, great intro video. But I want to re-watch it without the sound on this time and just take a look at what do you notice in this problem as the day goes on and the sun changes position. Look at the statue, or the shadow of the tree and the shadow of the street sign. They move in sync, and they kind of seem to grow and shrink in sync. They follow each other. And you can use those shadows, and you can use the fact that the sun's rays are creating those parallel lines to say the shadow and the height of the item are forming similar triangles. So we can use this idea of indirect measurement to find a missing height. All right, so our first example that we're going to look at here, we've got this tree that casts a shadow that, I don't know, looks like a big puddle of tar, but that's its shadow. And then we've got the sign from the men's bathroom. But we've got a man who's 6 feet tall, and according to this, his shadow is 9 feet tall. So we've got these similar triangles. We've got a shadow of 54 and an unknown height on the tree, shadow of 9 feet for the man, and a height of 6 feet for the man. So let's go ahead and set up and show a ratio. The height of the man compared to the length of his shadow is equal to the height of the tree over the length of the shadow of the tree. So from 9 to 54, that's a times 6. If the shadow is 6 times bigger, that means the height of the item we're looking at has to be 6 times bigger. 6 times 6 is 36. So we would say that this tree is 36 feet tall. And some of you might have noticed that before we even set up the proportion. If you're just wanting to find the scale factor directly by looking at the shadows, the shadow of the tree, 54, is 6 times bigger than the shadow of the man. So if their shadows are 6 times bigger, then the height also has to be 6 times bigger. And you can do it directly using the scale factor rather than filling in the piece of the ratio. It's whatever system works better for you. All right, we've got a fire hydrant and a lamp post, both casting shadows. It says find the height of the street light that casts a 24-foot shadow if the fire hydrant is 1.5 feet high and casts a 4-foot shadow. So again, we can start by just looking at the scale factor if we wanted to. The shadow of the hydrant is 4 feet. The shadow of the light post is 24 feet. So think, what is that a scale factor of? It's times 6. Again, the lamppost shadow is 6 times bigger than the fire hydrant shadow, so that means the light post has to be 6 times taller than the fire hydrant at 1.5 feet. 1.5 times 6. 6 times 5, 30. 6 plus 3, 9. Bring down 1 decimal place. So the light post is 9 feet tall. Those of you who are mental mathies, remember that we could think 1.5 and 1.5 is 3. And if I need 6 of those, that means I need 3 of these. 3 times 3 is 9. For those of you who like a different way to calculate and aren't multiplication gurus. All right, how about in terms of a word problem when the triangles aren't drawn for us? Can we do that? We sure can. Problem says Mimi knows that a plum tree is 8 feet tall, casts a shadow that is 15 feet tall. So we've got an 8-foot tall tree casting a 15-foot long, pretty wobbly shadow. She wants to calculate the height of a nearby willow tree. So I guess plum trees are maybe shorter and willow trees are taller. So here's my willow tree. The shadow of the willow tree is 30 feet long. How tall is the willow tree? So we don't really care about the hypotenuse other than knowing that's the sun shining down and casting the shadow. We've got a ratio of 8 to 15 equal to, excuse me, something over 30. We're comparing the height of the tree over the length of its shadow. Height of the willow tree is missing, so we leave this blank, and the length of its shadow is 30. To get from 15 to 30, that's a times 2. Whatever we do to the denominator, do the same up top. 8 times 2, 16. So this willow tree is 16 feet tall. That's a pretty tall tree. Okay, now here's one for you to try. I've got a flagpole that has an unmarked height, so you're going to be figuring out the height of the flagpole. A person, a kid, I guess, or man, who's 6 feet tall. The man is 6 feet tall. He's casting a 10-foot shadow. 6-foot tall guy casting a 10-foot long shadow. The flagpole, again, we don't know how tall it is. That's what we're going to solve for. But the flagpole is casting an 85-foot shadow. So use the notes that I know you've been taking from the previous examples. Copy down this example and think about how you would do it and go ahead and solve for how tall is the light post. So right now you need to pause the video, do the work on your own, and then you're going to come back and resume. Don't just wait for me to give you the answer. I know you're going to be tempted, but you got to pause it. Pause it. Did you pause it? Pause it. Okay, so you paused the video, you did the work. Now let's look at how do we solve for this flagpole. Oh, switch to pen. So we said the guy is 6 feet tall. His shadow is 10 feet long. We're trying to figure out how tall the flagpole is when it's casting an 85-foot shadow. So now some of you, it might jump out that 10 and 85, that's a difference of 8.5 times bigger. But for others of you, it might not. So we can simplify 6/10 down to 3/5. And we can go over here and say, what do I need in order to make 3/5 equal to something over 85? So if that's easier, we're going to think, okay, how many 5s are in 85? And we could do a quick division problem over here if we wanted to. It's pretty sloppy. But there's 17 5s in 85. So we're going to do 17 times 3 because this is times 17. This is times 17. 17 times 3. 21 plus 2 is 51. Okay, I said 51, I wrote 50. 51. So we're going to say that this flagpole is 51 feet tall. All right, so hopefully we've gotten some more good practice on how to solve for missing sides and similar triangles, and you've seen a context that's pretty common in problem solving where they ask you to do these triangles with shadows, and they call it indirect measurement. So up next, what I want you to do is IXL 7th grade, section X 13. I want you to spend 25 minutes. So look at the time right now as you're wrapping this up. When you get over to IXL and you find the correct section, notice the time, even write it down if you want. I want you to spend 25 minutes on X13. If you get your score to a 90 before the 25 minutes is up, you can try the Algebra 1 section. So when you go to grade levels, Algebra 1 is the one that comes after 8th grade. Try Algebra 1 F.7. It's going to be the same concept, but maybe with a little bit trickier numbers. When you've completed 25 minutes, you've gotten a 90 and hopefully the 7th grade version of this and had a chance to try the algebra version, then we'll move on to the next thing.